I'm going to speak briefly today about supporting all learners to use knowledge to make sense of the world in which they live. So what will we accomplish today, or what do I hope we will accomplish today? I hope I'm going to speak about how we can change classrooms to support all learners. And I know this conference has a special emphasis on promoting females and going into STEM and promoting their learning. So you can see the images of the various females that I work with, both at the elementary level, middle school, and high school level. We're then going to go into what is project-based learning, just briefly, because we don't have a lot of time. I'm going to talk about two projects that I'm involved in, multiple literacies and PBL, as well as crafting engaging science environments that both make use of project-based learning. I'm going to talk about the results of efficacy studies related to these two studies, and how the females, the women in the project, fared on them compared to males. And then hopefully we'll have some time for questions and discussion. So what drives me? What's my driving question? And so I've been driven since I've been a classroom teacher back in 1976 by how can I change classrooms to promote learning environments that foster engagement, creativity, and learning. And so I want to move away from the image that you see on your left with the young lady falling asleep, the guy in the back not really caring, to what we see on the right, where kids are really actively engaged in the learning process. And not just doing activity, but really involved in meaningful work where they're really learning important ideas for their future. So as I said, I'm going to speak primarily about two projects that I've been involved in. The first one is crafting engaging learning environments, or CELE for short. So it should be science, not learning environments. But anyways, so it's a five-year project supported by our National Science Foundation. It focuses on high school physics and chemistry and uses a project-based learning approach to really focus on helping kids meet standards that are based upon knowledge and use, to get kids to use their knowledge, not just know their knowledge, but be able to use their knowledge in new situations that they're presented with. Then there's the multiple literacies and project-based learning project, MLPBL, is a 5-year project supported by the George Lucas Foundation, and that's at the elementary level. But once again, we focus on knowledge and use learning goals, because we want learners to be able to use their knowledge to make sense of the world in which they live. So what's our challenge? What's my challenge? It's to build these learning environments that allow all students, and particularly females, as you see on the right here, to foster deep, integrated, and usable knowledge of science, but also to have the motivation to learn more science, to develop scientific practices so they can actually apply that knowledge in new places, as well as competencies like knowing how to speak, knowing when to use evidence. And finally, that these learning environments have to promote solving problems, making decisions, and thinking innovatively and imaginatively, or you might say creatively. So what's our solution? Our solution is to design, develop, and test a system for advancing science teaching and learning that builds on a vision for enacting project-based learning and meeting the NGSS for all learners. NGSS are standards within the United States that really focus on having kids apply their knowledge. And the system that we have actually has several components to it. One is that it has highly developed and specified educative teaching materials, but they're not prescriptive. So they gives teachers ideas on how to carry out the lesson, but in no way are they prescriptive. There's also highly developed and specified teaching materials, which allow kids to have firsthand experiences with phenomena and engaging them in a variety of scientific practices like constructing models and writing readings and writing about their experiences. The third aspect of the system is long-term professional learning that consists of both face-to-face meeting, video conferencing, and educative supports. And by educative supports, I mean showing the teachers, promoting their learning about how to take part in complex practices in their classroom, like engaging kids in writing scientific explanations with evidence, as well as modeling. And the last component is three-dimensional or knowledge and use, formative, and end-of-the-year assessments. And then we conducted an efficacy study because we can create materials that we think are good, but unless we really do an efficacy study that really shows if kids are learning, if the students are learning, then it's not going to move forward. So what is project-based learning? So project-based learning, in project-based learning, students pursue solutions to a driving question, a question that they find meaningful in their life, that creates a sense of wonder and a need to know. And I'll give you a few examples in a couple of minutes. We also focus on key learning goals. And as I said, these learning goals are knowledge and use learning goals because we want students to be able to apply their knowledge after they leave us, not just pass a test, which is important, but we want them to be able to use their knowledge as they continue in schooling and as they move forward in their lives. Students explore the driving question by experiencing phenomena firsthand. This is such a key aspect of what project-based science is. And then they participate in authentic, situated inquiry, making use of scientific practices in order to answer that driving question and make sense of that phenomena. Students have to engage in collaborative activities to find those solutions to the driving question. For instance, they build models together. They build a variety of products that represent their knowledge. And they use a variety of technologies, and we provide scaffolds actually to support students in participating in activities normally beyond their ability. And lastly, as I already mentioned briefly, they create artifacts. So artifacts in many respects can be thought of as tangible products that actually are embedded assessments because they give us insight into what kids have learned, but they also allow for choice and they address the driving question. Those elements, choice and is so critical in really promoting kids' ownership and drive to learn. So many of the features of project-based learning, like the driving question and experiencing phenomena, which then allows them to ask their own questions, engaging in inquiry to answer those questions, and the creating of artifacts in which they have choices to select, really promotes kids' ownership and a deep drive to want to continue to learn. So this is a bit of a representation about how is project-based learning different than traditional instruction. So in project-based learning, the figuring out process, making sense of phenomena, is driven by phenomena, and it creates optimal learning moments, right? So when kids experience phenomena, and I use the term phenomena frequently, but think of phenomena, and you may know, of course, because you're all science educators, they're events in nature that we can observe and we can investigate, and we have to be able to explain them. So for instance, in Michigan this year, spring came very early. That's a phenomenon. Why is that? How can we figure that out? So experiencing these firsthand phenomena gives rise to questions. Those questions can be the driving question of the unit, but those experiences and that driving question allow students to ask their own questions, and that propels or drives the need to find solution to the overall driving question of the unit. That then leads to students using a variety of different scientific practices, investigating, developing models, constructing explanations, analyzing data, using mathematical thinking. That then leads students to have figured something out. They now know something new. Students develop new ideas that help them explain the phenomena and go on to ask new questions. So project-based learning is not like traditional instruction because it really is anchored in kids making sense of phenomena or problems in their own daily life. So here is our logic model that drives the development of all our units and what we hope to learn as a result. So this model promotes both, is useful both for crafting engaging science environments as well as multiple literacies and project-based learning. And so we see on the left what drives this work are the features of project-based learning, and then the knowledge and use perspective, the integration of major ideas, disciplinary ideas, and scientific practices. That helps us create our PBL system approach, which includes, as I mentioned before, teacher and student materials, professional learning, and assessments. And of course, those all interact with the learning context in which we're in. And of course, prior to this year, we were primarily in face-to-face, but this year we're faced both with virtual communication, virtual teaching, as well as hybrid teaching. This then leads to both engagement, both in the teachers and the students. And the reason why is because the materials are both challenging for students. The students see some degree of challenge, but so do the teachers. But there's also interest in them. Students are interested in the driving question. The teachers are interested in the driving question. And more importantly, the teachers are interested in seeing the kids get excited. And of course, the materials also have a degree of they come in where the kids have a level of competency and they have to develop that competency further. This then leads to our outcomes, which is both academic learning as well as social emotional learning, enjoyment, curiosity, and ownership. So as I explained all these ideas already, but I'll just do them quick. Our whole system starts off with the features of project-based learning. Then we have the 3 dimensions of scientific knowledge, disciplinary ideas, scientific practices. In the US, we also use this notion of cross-cutting concepts, which are ideas like cause and effect, patterns, system models, etc. And as I mentioned, we develop highly specified and develop materials for both teachers and students. We create assessments, and we also have these long-term professional learning environments. So here are some examples of the units. Both the first one you see here are the example units from crafting engaging science environments, and these are the chemistry units. And you can see down the middle here are some of the driving questions of the unit. I'm only going to pick one, and hopefully you have access to these slides. If not, I can send them to you, and so that you can learn more about them. So I'm going to pick the second one to explain further, which is why is table salt safe to eat, but the substances that form it are explosive or toxic when separated. And of course, the phenomena here is taking something like sodium and placing it in water and having kids actually experience that, right? It's such an exciting thing for students to experience a metal that can be dropped into water and just reacts explosively. And of course, it's tied to these really challenging learning goals that you see on the left-hand side, which I like to refer to as performance learning goals, because kids have to do something with it. So I'm just going to explore one of those performance learning goals, which is use the periodic table as a model to predict the relative property of elements based on the pattern of electrons in the outermost energy level of atoms. Now, I picked this example on purpose because for us who are chemists, this is really a big idea for us in chemistry, that the periodic table allows us to make predictions about how materials behave. And so PBL, project-based learning, can actually get at kids understanding some of the deep understandings that we always hope kids could develop in our normal traditional classes. These are the high school physics units for crafting engaging science environments. Again, you can sort of see the driving question. I'll just pick one for, again, just to quickly go through it, which is the first one up there. How can I design a vehicle to be safer for a passenger during a collision? And of course, this is a kid's experience through video. We don't actually have them collide on anything. What happens when vehicles are moving at high speed and they crash? And of course, this allows us to get into really important performance learning goals related to Newton's second law. These are some of the ML-PBL units. I picked the ones from the third grade, but we have materials for both third, fourth, and fifth grade. And I'm just going to pick one of these. I'm going to pick toys, the second one there. And you can see the driving question there is, how can we design fun and moving toys that kids can build? Now, this unit deals with very sophisticated ideas for third graders. In fact, the basic principle underlying this whole unit is having kids understand how balanced and unbalanced forces are important in making things start, stop, change direction, or if it's balanced, then it's just going to keep doing what it's doing, either moving at a constant speed or just standing still. And I also put examples of the final artifact here. I don't have time right now to go into the learning goals, but they are at the end of the slides. So if you get the slides, you can actually look at what those learning goals are. So I'm now going to talk about a quick study design. The design was very similar across both projects. They were both randomized controlled treatments. They were matched randomized control treatments. And so we picked one school, and then we had to find another school that was an exact match to it. And we collected a variety of different kind of data, including objective pre and post measures of science achievement. We observed the teachers to get a measure of fidelity of implementation. We surveyed both the teachers and students about what they thought of the units. We also measured social and emotional learning that I can't get into today, and we interviewed teachers and students. Now, what I don't have down here, and I should have down here, are the summative tests. We also collected summative tests, but we did not create the summative tests. The summative tests were done at the end of the year. So we had tests that were done after each unit that we created, but the measure that you're going to see in the next slide was designed by a third party. In our case, it was actually the state of Michigan who developed tests for the state of Michigan to see, are the kids meeting what they're supposed to meet with these new standards? So here's the results of the randomized control trial. And I'm first going to talk quickly about crafting engaging science environments, and then I'll move on to the ML-PBL. And in the crafting engaging science environments, we use schools both in Michigan and California. Once again, they were matched. You can see that we used with a large number of teachers and students. We had a very large effect size of 0.21, which is large when you have a randomized control trial. And this accounted for a 7% increase difference between the treatment in favor of the treatment group and the control group. That's like moving kids from not being proficient to being proficient, or from being proficient to highly proficient, which is a substantial increase in their knowledge. The same thing is true of the multiple literacies and project-based learning. In this case, though, we only worked with schools throughout the state of Michigan. And you'll see here that once again, we got this a slightly larger increase. It was an 8% increase. And what's really important about this increase and how this study was conducted is that the results are actually generalizable to the entire state, even though we didn't work throughout the entire state because we did such a careful job of randomizing and controlling the randomization. It's actually generalizable to the state and to a number of other states within the United States. Now, critical to the theme of this conference, which is promoting women in science, these results are consistent across gender, race, ethnicity, and reading ability. What does that mean? That means that if you're a male or a female, you scored just as good as the guys did, irregardless of your race, your ethnicity, or your reading ability. That is a tremendous finding, right? There was no gap between women and men, any statistical gap between the females, either in crafty and engaging science environment or the multiple literacies and project-based learning. You can see that a little bit more in this slide. Females in the treatment group significantly outscored females in the control group. And yet they were also similar to the performance of males. This is an important finding because this is how, over time, if we work in elementary classrooms and middle school classrooms and high schools, this is how we're going to narrow the gap both between females and males and promote females going into various STEM fields as much as males. And it's significant because our work was done in chemistry and physics, and typically you don't have a lot of females succeeding in courses like physics. So what are some major takeaways? So science academic performance can be improved with an intervention that is created and implemented as a coherent system, which includes both teacher and student learning experiences in which they make sense of phenomena, teacher professional learning, and I have to stress sustained teacher professional learning, as well as formative and summative unit assessments that involve science practices. Critical to our work is that our system works for all genders, races, and ethnicity. Our work has been vetted by various academic journals, Yale and Harvard University Press, and the results of the efficacy study are still currently under review. But we actually sent them out to some really good scholars to get to critique them, and we got really good feedback on them. And so I'm sure they'll be published in the near future. We have performance-based learning goals, which is critical for principled project-based learning science reforms. And lastly, science needs to take place, needs to have an equal place to reading and mathematics in K-12. We stress this in our work. I didn't talk much about it today. So a concluding message, project-based classrooms become learning environments where teachers and all students, including females, can engage in science to design and carry out investigation, to make claims, to make and debate claims supported by evidence. It provides a very engaging learning environment. And as the data has shown, it can very clearly increase their academic performance. And finally, we also have data that shows that it fosters imagination or creativity, problem solving, engagement, and their ability to communicate and work with others. So that's the end of my presentation, a couple of minutes longer than I had hoped, but now we at least have a couple of minutes for questions if there are any questions.
Thank you very much, Professor Krajcik. So now we encourage the participants online to put your questions on the chat box. And now I'm open for questions for the on-site audience. So anyone? Yes, please. Yeah. Maybe pass the microphone. Joe, we have a participant to ask the question. Yeah, it's on. Yeah.
Okay. Thank you very much for your remarkable speech, Professor. I have two concerns from your speech. The first is I would know more details about what is 3D dimensional formative assessment you mentioned in your solution slide. And the second is that because most of teachers, no, a lot of teachers, they have problems when they find the project-based learning topic, which are authentic phenomenon, but also align well with national education and educational standard. So do you have meet any barriers to find the topic, and what is your solution? Thank
Okay,
you.
I'll answer the first one first, and then I'll get back to the second one. Okay, so the first one, and I apologize that I did not explain it clearly. In the United States, we have this phrase called three-dimensional learning, and what that means is that when you in the past in the United States, standards were basically focused on knowing a particular content knowledge, right? So students will know that when a chemical reaction occurs, new properties emerge. But there's been a lot of research and theoretical ideas about just what does it mean to know. And if all you focus is on just knowing, kids won't develop knowledge that they can use later on. And so the focus has been changed to these knowledge and use standards or performance learning goals. And so what we do now in the United States is we integrate scientific practices with a big science idea, along with these things called cross-cutting concepts, which are ways are scientific ideas that scientists and anybody who's trying to figure out phenomena basically use, like cause and effect, like systems model, like patterns. And so if you look at that first learning goal, I said, students know that when a chemical reaction occurs, new properties are formed. That doesn't exist anymore in the United States. Now we have a performance learning goal or a three-dimensional learning goal, which states something like students will construct a model. That's a practice or a performance that when a chemical reaction occurs, that's the big disciplinary idea, it causes, which is the cross-cutting concept, new properties to emerge, right? So that's what three-dimensional learning is. And I hope that makes more sense. And if you actually look at all the performance learning goals, you will notice how they're broken up into those three parts. You'll see a practice or a performance. You'll see a disciplinary idea, and you'll also notice cross-cutting concepts in them. And you're absolutely right, project-based learning is different than we normally do in classrooms. And it's a switch from the way we were taught, and it's a switch from how most teachers have been taught. So it's going to take us a while to learn actually how to do this in classrooms. And this is why I kept stressing that long-term professional learning is so critical. You just can't give them a one-day workshop. It has to be, in our work, we do 3 or 4 days during the summer. We meet with them either through video conference at least every other week to be able to answer questions. And then we also have, before each new unit, another whole day face-to-face meeting. So and we're also available on email if people want to reach us, right? So there's a variety of ways in which teachers can learn. And it's not, it is challenging. Teachers have to have new practices. They have to know how to support kids in collaborating. They have to know how to support kids in building models. So all this takes time to learn. But the results are pretty clear. If we really want to promote kids who are more engaged in learning and actually do better, project-based learning works. Those results, these results should be pretty convincing about that this is a better method. If it wasn't randomized, I would say you could question it. But this is a wonderfully randomized controlled trial, just like all the randomized controlled trials we hear nowadays about the vaccines. And so this is pretty strong evidence that if we want to get kids to be able to learn more, be more interested in science, then project-based science works. But again, it's not just the materials, right? That's what I was trying to stress all along. It's not just the materials. It has to be the materials, it has to be professional learning, and it has to be the assessment. And that's what promotes the learning.